In this video, we will talk about Young's double-slit experiment. One day, they asked a bunch of physicists to rank the most important experiments of all time, and this experiment ranked in the top 10. Right? This is an experiment that was made in 1801 by Thomas Young, an English scientist, and the reason this is such an important experiment is because it showed that light has wave properties. Right? In Young's experiment, light behaves as a wave. And before we do Young's experiment with light, we're going to do this experiment with water. In this demo, I have a small bath of water, and there is a motor that creates water waves by oscillating a black rod. Then we have a bar with silver color with two gaps in it. And the two gaps are like two sources of water waves. And below the water bath, there is a mirror at 45 degrees to project the image on the side widescreen in the front. Now I'm turning off the light so that the waves are easier to see on the screen. I'll adjust the position of the gaps, and now you can see the waves. We can see better in slow motion. During the video montage, especially with the slow motion, I realized that the two arms for the oscillating rod are not exactly in phase, so we can see a small phase difference for the waves coming from the two gaps. It is not very big because we can see constructive interference at the center between the two gaps, but still, if you look carefully, it's not exactly at the center. Unfortunately, I did not notice this before recording the video. But the important result is that you can see there are directions for which we can clearly see the waves. Those are the directions for which the two waves from the two gaps interfere constructively. So the phase difference between them is 0, or 2 pi, or 4 pi, or 6 pi, and so on, so that their maximum or minimum coincide. This creates waves with double amplitude. And you can also see directions for which we barely can distinguish any waves. Those are the directions for which the two waves from the two gaps interfere destructively. The phase difference between the two waves is pi, or 3 pi, or 5 pi, and so on, so that the maximum from one wave coincides with the minimum from the other wave. And this means they cancel each other, and we cannot see the waves. Now, let's look at the same experiment with light, light from a laser. I have a plate with various kinds of small slits in it, and I'm going to shine the laser on two slits that are very close together. So let's see what happens when I do that. I will turn off the light and shine the red laser on the plate. Now let's look at the laser spot on the board. You can see what happens when you get old. Your hands are not very steady, but here it is. You can see that there are dark fringes in the laser spot. You have a central bright spot, dark fringes, and other bright spots on both sides. Right? So we are seeing constructive and destructive interference, but with light. Right? This experiment and others that we will see later shows that light has the same kind of behavior as water waves. In fact, light is a wave of electric and magnetic field. Here is a schematic of Young's experiment. In the demo we just did earlier, the slits were vertical, so we obtained bright and dark fringe in the horizontal direction. In this schematic, the slits are horizontal, so the screen has bright and dark fringes in the vertical direction. But in fact, if you know that light has wave properties, then you can already know how to explain this experiment. We have two slits separated by a distance d, and a screen that is located at a distance L, and we are looking at a point of the screen that is at a position Y. This point receives waves from the first slit, and the path of the light is R1, and this point also receives waves from the second slit, and the path of the light is R2. And we have seen before that what will be important is the difference between R1 and R2. So to calculate the difference, there is a simplification that we can do in this situation. where the screen is very far from the slits. So and the slits are very close to each other, then you can assume that the two rays of light are parallel to each other. In this case, then the two rays make an angle theta with the normal from the slits, and the angle is the same for both of the rays, right? Just theta. And with this simplification, the difference between R1 and R2 is simply this little extra length highlighted in red here. And this length is equal to d sine theta. So the path difference is equal to, when this path difference is equal to m lambda, with m any integer number, then we will have constructive interference. And if the path difference is equal to m plus 1/2 lambda, again with m an integer, then we have destructive interference. And this gives you the angle theta for which we see a bright fringe or a dark fringe. And we can calculate the position on the screen from this angle, right? To do this, we have the position on the screen y, which is equal to L tangent theta. And for small angles, that means if y is much smaller compared to L, then tangent theta is almost equal to sine theta. And so the bright fringes will be at the position y equal L m lambda over d, with m an integer number. And for the dark fringes, they will be at the position y equal L m plus 1/2 lambda over d. Now, before we continue, I should mention that in this chapter, we completely ignore the size of the slits, right? We assume that the width of the slit A is much smaller compared to the separation of the slits D, right? A is much smaller compared to D. We will come back to this approximation later in this chapter. Now, these formulas that we have seen so far, they give us the position of the bright fringes with maximum intensity and the position of the dark fringes with zero intensity. But what is the intensity in between, right? At intermediate angles, at intermediate positions. In the next part, we will consider the intensity at any position on the screen. So to calculate the intensity, we're going to use the relation between the intensity and the electric field. The intensity of a sinusoidal electromagnetic wave in vacuum is equal to 1/2 epsilon 0 c e squared, where in this relation, epsilon 0 is a constant called the permittivity, c is the speed of light in vacuum, and E is the electric field. In fact, you really don't need to remember this formula. The only thing that we need is that the intensity is proportional to the square of the electric field, right? Remember, we've already seen that the intensity of mechanical waves is proportional to the square of the displacement. For sound waves, we have seen that the intensity is proportional to the square of the pressure fluctuations. And now you see that for light waves, the intensity is proportional to the square of the electric field. And this is because light is in fact a transverse wave of electric field and magnetic field, with the electric field perpendicular to the magnetic field, and both the electric field and the magnetic field are perpendicular to the direction of propagation. So we have the electric field from the first slit, which will have the form E0 cosine omega t, and E0 is simply the amplitude of the electric field oscillation. Then we have the electric field from the second slit, that is E0 cosine omega t plus delta phi. Delta phi here represents the phase difference between the two paths, right? It is equal to k delta x, and we have seen that delta x is equal to d sine theta. So delta phi is equal to k d sine theta. Now we can use the principle of superposition and write that the electric field is equal to the sum of the two waves E1 and E2. And so it is E0 times cosine omega t plus cosine omega t plus delta phi. Now, once again, we're going to look for a trigonometric formula. And we have the sum of the two cosine functions here. So that is 2 cosine of the average times the cosine of the difference divided by 2. So we obtain 2 E0 cosine of 2 omega t plus delta phi over 2 times cosine of delta phi over 2. So the square of the electric field will be proportional to the square of the two cosines. And the first one will oscillate between 0 and 1 as a function of time because it contains omega t. Right? So the average over a full cycle will give you a constant. And since the intensity is proportional to the square of the electric field, then the intensity will be equal to I max times cosine square of delta phi over 2. And this gives you the intensity for any angle theta with delta phi equal kd sine theta. There is a useful plot of this function to remember. The cosine square function will have a maximum every time delta phi is equal to 0 or 2 pi, 4 pi, and so on. And since delta phi is equal to 2 pi over lambda d sine theta, then there will be a maximum intensity when d over lambda sine theta is an integer number, right? Or when sine theta is equal to m lambda over d. And so on the plot of the intensity, we have a maximum for 0, plus or minus lambda over d, plus or minus 2 lambda over d, plus or minus 3 lambda over d, 4 lambda over d, and so on. And this will happen as long as m lambda over d is smaller than 1, right? Because remember, sine theta is between plus or minus 1. So this plot will be useful to solve a lot of problems quickly, so try to remember it. For those of you who like graphical representations, there is a nice trick to deal with the additions of cosine functions, right? This technique uses an arrow called the phasor to represent the phase in the cosine function, right? So in the cosine function, you have omega t plus delta phi and so on. So we represent this as an angle. And if you have two cosine functions and the second one has an additional phase of phi compared to the first one, then the second arrow is rotated by an additional angle of phi, right? Because the phase also contains omega t term, you need to imagine that these phasors are rotating with an angular frequency omega. But what we care about here is the addition of these two phasors, which is represented by the red, by the length of the red arrow. You see that if the phase difference between the two phasors, phi, is equal to 0 or 2 pi, plus or minus 2 pi, plus or minus 4 pi, and so on, the two phasors are going to be aligned. And the red arrow will have the maximum length possible. And this corresponds to the maximum amplitude. And since the intensity is the square of the amplitude, it corresponds to the maximum intensity. And when the phase difference is equal to plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, and so on, then the two phasors will be canceling each other, right? Because you have an angle of 180 degrees between the two. So the amplitude, which is represented by the sum of these two vectors, will be 0, and so the intensity will also be 0. And this technique will be very powerful when we will need to add more than just two phasors.